Let us start our today's scientific voyage with the introduction of a very distinguished speaker, Professor Satya Atluri, who is coming from the University of California at Irvine. Professor Atluri's wish, as you have seen, is that I present him in a brief way. However, I have to admit that this is a very complicated task. He is currently holding position of the director of the Center for Aerospace Research and Education, and in addition to that, he is holding positions of distinguished professor at the Indian Institute of Science, honorary chair professor at National Tsinghua University in Taiwan, honorary professor at Tsinghua University in China, adjunct professor at the Advanced Institute of Science and Technology in Korea, visiting professor of the Hong Kong University of Science and Technology, distinguished fellow of the Japan Society for Promotion of Science, and consulting professor at the Emei Tong University in China. Previously, he has held positions of Samuel Theodorfer Kahneman Chair in Aerospace Engineering, University of California, Los Angeles, and he was one of the 6 institute professors ever elected in 150 years of history of Georgia Tech in Atlanta. Professor Atluri graduated and obtained his master's thesis at the Bangalore University, India, and in 1969 obtained a doctorate at MIT in the USA. Both his master's and his doctoral thesis were rewarded as exceptional and represented a foundation for an impressive scientific career, which reflected in the authorship of over 700 scientific articles, the authorship or editorship of some 50 scientific books, and in the mentorship to approximately 300 graduate students and postdoctoral researchers, and in the ranking among the 100 most quoted authors from all fields of engineering. Until the end of the 90s, Professor Atluri handled mostly the development of finite and boundary element methods for elasticity, hyperelasticity, fatigue, and fracture mechanics, biomechanics, and fluid mechanics. One of his fundamental achievements from this period is the development of the theory and use of connected simulations at a microscopic level with a macroscopic scale, which opened up the path, for instance, for the design computer simulations of the aging of aircraft and the strength and reliability of the pressure vessels of nuclear reactors. Afterwards, he contributed fundamentally and in a pioneer way to the development of meshless numerical methods with the establishment of the local Petrov-Galerkin method. The later field was recognized in 2004 as the 3rd fastest developing field among the 108 from the area of computer science. His clear and systematic textbooks, which are also used by our students, represent classic educational works in the field of computational mechanics. Professor Atluri is a member of 6 scientific academies: US National Academy of Engineering, Indian National Academy of Engineering, European Academy of Sciences, Ukrainian Academy of Science, Korean Academy of Science, and the Third World Academy of Science established in Thirst. For his work, he received some 20 prestigious awards and acts of recognition in the USA, numerous other countries, and internationally. Let me point out a few of them. Structural Dynamics and Materials Medal, as well as Pendry Aerospace Literature Award, both awarded by American Institute of Aeronautics and Astronautics. Aerospace Structures and Materials Award, awarded by American Society of Civil Engineering. Outstanding Achievement Award, awarded by US National Academy of Engineering. Computational Mechanics Division Medal, awarded by Japan Society of Mechanical Engineering. Ehringen Medal, awarded by Society of Engineering Science. He has received honorary degrees from the academic institutions in Greece, India, Ireland, and Slovakia. His achievements opened him doors to Indian and American leaders. He was advisor of Prime Minister of India, the late Mr. Rajiv Gandhi, to discuss India in the year 2000, and advisor of President Clinton's Committee for the National Medal of Technology. He also served several times in Nobel Prize committees. He is particularly important and active in the field of connecting sciences and engineering. For this purpose, he has established ICCS, an international forum for computational engineering and sciences, which annually organizes an international meeting at which numerous Slovenian researchers are present as well. In addition, he has designed and started 6 international journals which border on both fields, among others the computer modeling in engineering and sciences, which belongs to the very top of professional journals in the field of interdisciplinary engineering. This year, he has organized in Slovenia, in cooperation with our university, an international symposium on meshless methods. I will now give the floor to Professor Atluri. Let us enjoy his lecture on computer modeling of phenomena that bridge the scales from mega to nano.
Thank you. Thank you. Anyway, I'm an engineer by training and profession. And I started out my graduate school when computers were just coming to be used. And I remember the days where we used to punch a lot of cards and submit them to the computer center and come back 3 days later to see what the results were. So I have grown up with computers, and essentially in those days we didn't call the discipline computer modeling, and indeed we did not know what to call that discipline. So we kind of floundered around using analog computers and digital computers to solve problems. And so in the intervening 40 years or so, this discipline has matured, or at least become a recognizable discipline. And in the beginning, it used to be called computational mechanics, but soon it turned out that it was computational mechanics was kind of a limiting title. So I coined the word computer modeling in engineering and sciences, and now I think this is more or less recognized as a discipline within applied mathematics and at the interfaces between engineering and sciences. And so the title of my lecture, From the Mega to the Nano, Computer Modeling in Engineering and Sciences, essentially is an attempt to show how computer modeling in engineering and sciences is used to devise or design devices that operate at various length scales from mega to the nano, and how in the last few years and in the coming decades, this discipline would play a central role in changing our lives, especially at the interfaces between life sciences, engineering, and health sciences. So my lecture would be kind of very broad to give you an overview of how this discipline plays a role in our daily life and in the future in fighting diseases and so on and so forth. So if you start looking at engineering, the definition of engineering on Wikipedia or some other source like that, engineering is basically application of science, any science, life sciences, physical sciences, chemical sciences, any science, to cleverly design, construct, and operate structures, machines, and other devices of industry. And so basically, engineering makes economies run. And engineering is at the center of the quality of life and how the societies function. But of course, science is also at the center of everything. And so engineering and science go hand in hand, and engineering is essentially a clever application of fundamentals of science to create devices that would improve the quality of life, improve the health, improve the well-being of the society on a daily basis. And so engineering, can be at any length scale. So basically, in the beginning of human history, people were fascinated by cosmological events, and so big things. When we looked out into space, people thought about what was beyond us. And then in the last 200 years, we started building big things, big bridges, and space shuttle, or large airplanes, or what have you. And so this length scale is on the order of meters, large space structures on the order of kilometers. And then we started going down in the length scale and started building micro electromechanical devices that are basically chips that would do things more than computing, things that would be functional in a variety of ways in health systems, in labs and chips and life chips and so on and so forth. And then we went down in the length scale and found use for nano systems, carbon nanotubes, or things at the nano level, thanks to the lectures of Richard Feynman and others that opened our eyes to how to use atomic level or subatomic level devices to make things happen. And carbon nanotubes is a typical example of that. And then we go down in the length scale, and then we found quantum dots and so on and so forth. So basically, the engineering makes all these things happen, from very, very large systems to very, very small systems. And basically, if you look at the scientific underpinnings of all these devices, especially if you just look at mechanics, and the father of all this discipline is Newton, 1600s, and celestial mechanics and astrodynamics, and followed by Einstein and a whole bunch of others, Chandrasekhar and others. And then starting from the 1800s, or even starting from Newton, we have this discipline of how continuous media will behave, solids, fluids, and of course others have developed electromagnetics, thermal fields, and so on and so forth. And so this continuum mechanics of things that are fairly large, a meter, 100 meters, 500 meters, or a kilometer long. And then in this 1960s, this continuum mechanics gave rise to computational mechanics, the use of computers in using the theories of continuum mechanics. And the theoreticians that developed this subject are Truesdell, Eshelby, Reisner, Drucker, Hill, variety of these people. Some were very active in the second half of last century, and some of them were actually my teachers, and they taught a lot of other people. And then you had microscale mechanics, and mechanics at the microscale, 10 to the power of -3, -4. And of course, a lot of people developed these phase field theories, statistical mechanics, crystal plasticity, and so on and so forth. And so basically, and then you went down the length scale, and of course, Feynman and Smalley, and they opened our eyes to how nanomechanics can be used for building devices at the nanoscale. And essentially, theories such as molecular dynamics, lattice-Boltzmann method, Langevin dynamics, Monte Carlo, dislocation dynamics. All these are tools that enable these nano devices to be made. And then, of course, in the last century, Bohr, Fermi, and Schrödinger taught us how matter behaves, and quantum electrodynamics became an undergraduate subject. So if you go down the time history, starting from about 1600s to now, variety of theories, especially in this physics, I only mentioned physics, and you can say draw a similar chart in chemistry and biology, and I'll show you a biological chart momentarily. So in the last, couple of centuries, there is an explosion of the application of science in building things that society can benefit from. And of course, all these devices also function at variety of length scales, time scales. They operate anywhere from femtoseconds to nanoseconds to minutes, hours. And so basically you have variety of length scales, variety of time scales that these devices operate in. And if you take the biological and medical sciences, you have the same. You have a human body, a human organ, tissue, and if you go down the length scale, you have the cell, and then you have mesoscale, organelles, and then you have protein, and go down DNA, and so on and so forth. So basically, this is now the molecular and cellular biomechanics is now where the tremendous research is being carried out, especially in identifying diseases and so on and so forth. And engineering intersecting with molecular and cellular biomechanics or mechanics of DNA, RNA, and this is where computer modeling and engineering and life sciences would intersect and produce fantastic devices in the next few decades that would be unimaginably helpful to the human race or even other animal kingdom also. So if you look at the length scales, the biological systems also have variety of length scales. And if you look at the time scales of variety of biological processes, you have DNA twisting, protein motion, and so on and so forth, variety of time scales also. So engineers in the next few decades would have to study biology. Every undergraduate student would have to necessarily study biology and life sciences to be useful to society. So engineering will take on a different meaning, and its intersection with life sciences and health sciences would become more and more critical. And in this area is where computer modeling would play a significant role. And so if you look at mechanics, for instance, application of mechanics, you have quantum mechanics, molecular mechanics, mesomechanics, continuum mechanics, and systems engineering, spanning variety of length scales and variety of time scales. And even though in the last 2 decades, so-called multi-scale modeling has become fashionable, that means to model systems spanning variety of length scales, and only in the last few years we recognize that paradigm is not that much useful, except modeling systems within their own length scales. Modeling systems at the continuum level, modeling systems at the nano level by themselves would yield fantastic results that would make devices and engineering at those length scales possible. So it is not necessarily the multi-scale, seamless multi-scale modeling, the dream that in the last 20 years that has been shattered, but the modeling within each length scale to create devices at that length scale is a more achievable goal in the next 20 years, and that's where engineering would make significant contributions. On the other hand, bridging time scales is something that not necessarily very successful so far, and that's where future advances may be made. And if you look at biosystems the same way, you have a variety of biological systems that are DNA, proteins, organelles, cells, tissues, and organs. And then you have a variety of time scales, anywhere from protein motions to DNA motions. And then you have the same type of paradigm, quantum molecular mesoscale continuum, and again, modeling biological systems within a certain length scale, or maybe going one length scale beyond that, I think would yield significant results that are beneficial to society. So being an aerospace engineer by training, I want to illustrate how computational modeling has played a significant role in making aviation possible and making aviation safe. For instance, if you want to travel from Ljubljana to Los Angeles, you never think of taking a ship anymore. You always think of just flying, and you want to fly there as quickly as possible and as safely as possible. And so this idea of flight, which is only 50 years old, has dramatically changed society and how we think of ourselves as a world. And it has made it possible to be in California on Monday and to give a lecture in Slovenia on Tuesday and go back and teach my classes in California again on Friday. So this has made tremendous advances possible. So it all started not very long back. It started on 17th of December, 1903. And these are people that didn't have very much formal training, and they just were ingenious people, and they started this flight in 1903. And if you look at least the history as seen by the United States, it turns out that this flight of Wright brothers in 1903, if you go back and look at what all happened in 20th century, everything that happened in 20th century, it turns out that is the fourth significant event that changed the world completely. And so, of course, it's only 100 years. Now we talk about going to Mars. So now I would like to trace the history of just the civil aviation and maybe some military aviation for a few minutes. And so if you look at mega systems like an airplane and how since the 1950s the jet age has completely changed, and see the underlying methodologies that made it all possible, you would soon realize computer modeling in engineering and sciences, even though it was not called by that name in those days, but still computer-based methods, multidisciplinary optimization, and that means how you understand aerodynamics, propulsion, and structural safety. All these things put together, how do you do multidisciplinary optimization? And how do you integrate product and process design? That means how do you make every part in this airplane so that ultimately this big machine is safe to fly and it can fly safely for 20 years. This is an incredible achievement. And then damage tolerance analysis, virtual reality, these are all the underlying computer-based methodologies that makes aviation possible. And of course, about when I started out my own career, I did pieces of almost everything: multidisciplinary optimization, integrated product and process design, damage tolerance analysis, virtual reality. And so about 15 years back, I put together what all I knew at that time into a 1,000-page monograph which deals with most of these methods. So computer modeling is at the center of aviation industry. On the other hand, if you look at a simple a sample plane like a Boeing 737, even though I should not mention any commercial names, it turns out that this particular plane was traveling between two Hawaiian islands from Honolulu to Maui. And the flight time between Honolulu and Maui is half an hour. So this plane was taking off and landing 10 times a day or more times a day. And in an airplane, when you take off and land, for human comfort, you pressurize the aircraft. You pressurize the aircraft, and you depressurize it when you land. So basically, the cycle of pressurization and depressurization is a load cycle. So basically, when this plane was going from Honolulu to Maui 10 times a day, 365 days a year, it was putting 10 load cycles per day, 4,000 load cycles per year, and this plane flew for about 20 years in this way, so it put down 80,000 load cycles. So it was in one day in 1988, the top of this plane blew open on the flight from Honolulu to Maui. And so the reason for that was when the airplane was put together, it had fastener holes tying one sheet to the other. And these fastener holes were in a lap joint. So the lap joint was like so. The lap joint was like so. And so there were fasteners and fastener holes. And so very, very small fatigue cracks grew from these holes. And in 90,000 fatigue cycles, these small cracks grew and linked together to the point where the cracks propagated throughout the length of this fuselage, and the top blew open. And so that is the picture. After about 90,000 flight cycles, the top blew open, and the plane did land safely. But of course, whenever and unfortunately, one of the flight attendants was killed. She was simply sucked out into the air, and nobody found her. And so that completely shook up the civil aviation industry, and that started a Federal Aviation Administration research into aging of aircraft. And that is when I became involved in research on aging aircraft, and I directed a large center for aging aircraft at Georgia Institute of Technology for about 7 or 8 years until we solved the problem and attendant problems with aging. Then it became a problem of not only aging of aircraft, but aging of engineering systems in general, and how to cope with the problem of aging. It's just like human aging. What do you do when engineering systems age? So if you look at the life cycle of an aircraft and see how, as an example, and this can be said about every engineering system, no matter what, including an automobile, a ship, a bridge, whatever else you think about, but this is simply typically what happens. If you look at the age and the life cycle of an aircraft, a designer, a company will first look at market requirements, whether they need aircraft in China to fly short routes, or whether they need large aircraft to fly from one city in Europe to another city in the United States, or whatever market requirements. And then you have a design of a prototype, and that's where you use all the computational methods, finite elements, boundary elements, meshless methods, multidisciplinary optimization, inverse problems, and large number of people work on it. And So computer modeling plays a significant role. And in fact, if you look at Boeing 767, it was completely designed on a computer without any wind tunnel testing or anything else. And so you have all these computational methods playing a role in the design of prototype and certification. And then you have structural integrity and durability. How do you make sure that this airplane is safe? And if you have defects, how is the aircraft damage tolerant or safe or whatever? And then you have, companies working about scheduling the aircraft. And you may think scheduling is a simple task. But in reality, airline scheduling is a highly complicated mathematical problem. And just like scheduling of baseball games or soccer games or whatever, scheduling of an airlines, that means how do you get a person from point A to point B in the least time possible with as few stops as possible. That is a highly complex mathematical problem, and computers are used for years to solve that problem. And so airline scheduling is a very, very serious computer modeling problem. And same way, navigation and control, air traffic control and navigation, they are also algorithms based on very advanced mathematics. And then you have damage tolerance and life enhancement. That means as the airplane ages, how do you enhance the life of this aircraft so that its economic life would be extended? So mathematics and computer modeling plays a role throughout the life of this aircraft or throughout the life of an engineering system. So primarily we may conclude that in the life of an aircraft, this computer modeling and engineering and sciences is the dominant discipline that makes the aircraft systems run. Now, if you take an airplane and you do its aerodynamic analysis or stress analysis or whatever, you can see that you have a variety of numerical methods, computational methods, finite volume, finite element. These are all kind of methods that one was developed based on the other, one is an advancement over the other. So there is a pedagogical sequence of variety of computational methods. So you can do aerodynamics of the entire aircraft. You can do the stress analysis of the entire aircraft. And then you can start coming to a panel, and this lap joint I described, you can start zeroing in on the lap joint and see whether this lap joint is safe. And after you do the lap joint, the system level analysis, you can now go into the more local level analysis. Not all in a seamless way, but this is kind of divide and conquer. So when you come to this particular case, you're talking about a rivet hole in a lap joint. So you have analyzed an entire aircraft, you have analyzed a panel, and so you're coming in from one level systematically down to the next level. And ultimately, to make the aircraft safe and to make sure it is safe for 20 years and 100,000 fatigue cycles or whatever, you are going to look at a micro crack. So you are going from an aircraft that is maybe 100 meters long to a micro crack that is 10 to the power of minus 5 meters long. So mathematics and computer modeling plays a dominant role in making sure that this little micro crack near a fastener hole in a lap joint in an aircraft does not cause catastrophic failure of the aircraft in 18 years or 20 years or what have you. And then, of course, you do not want to make sure, you want to make sure that this analysis is not the only thing that you rely on. You have periodic inspections, non-destructive inspections, which again are mathematical. And wave propagation, electromagnetic waves or stress waves, and how to detect them. So as you can see, even though you fly an airplane and don't realize what's happening in the background, mathematics and computer modeling plays a significant role in every day of this aircraft. So you're going to monitor those micro cracks of 10 to the power of minus 5 from rivet holes rivet holes are like 0.1 inches hole. That means they are about centimeter, 0.5 centimeters, and to all the way to an aircraft. So modeling at every level is very, very significant. And success or failure of an aircraft and its operator depends upon all this modeling. So that's the reason why you can see certain aircraft are more successful than the others. And it is the lack of this analysis that led to the Comet failure and essentially the failure of the British aviation industry in the 1950s and this dominance of the American aviation industry starting from that point. So now everybody realizes that this multi-level analysis, mega to micro analysis to make sure that the aircraft is safe is essential for its operation. Okay, so if you were to then look at this micro level analysis near a fastener hole, you have a very, very tiny crack. And you want to make sure you understand how this micro crack will grow to destroy the integrity of the aircraft as a whole. So you need mathematical tools. What you find out is if you start out with micro cracks of variety of configurations and see which one is more critical, and you pretty soon find out from this modeling that this micro crack emanating from the fastener hole, this is the fastener hole, this is the countersunk rivet, and this crack emanating from it will grow in fatigue like so, and it will become through the thickness crack, and it will become, this is the thickness of the aircraft skin, and it will, after 40, 50,000 cycles of fatigue, it will become a through the thickness crack, and it will start propagating in the length direction. That's what happened in this Aloha Airlines. The crack started propagating along the length of the fuselage, and the fuselage ultimately failed. So how do you analyze this? Of course, you need a complicated mathematical model. As I said, this was done by an MLPG, symmetric Galerkin, boundary node method. These are all gobbledygook in the vocabulary of what we do every day. But it doesn't matter. These are efficient mathematical techniques to model on the computer how this little crack will propagate in the rivet hole and through the thickness and ultimately make the aircraft unsafe to fly. And this is what the experiment will tell. Essentially, this is the crack in the analysis, and this is the crack in the experiment. And ultimately, in the experiment, the crack has gone through the thickness of the rivet hole, and it has become like so. So as you can see, computer modeling can simulate reality quite well. And this is, this is one slide, but what went into it was the work of at least half a dozen very smart young men and women to come up with the right mathematics and the right modeling to the point where this particular program detail is very widely used in the US government and the US industry for fatigue estimation of life of systems. Now, if you consider a helicopter is designed only to run only for a few thousand hours. Its life is only a few thousand hours. A helicopter is also known, at least in the circles of engineers, as a fatigue machine. It generates fatigue. It's constantly generating fatigue, high cycle fatigue. So that's the reason the structural systems, the systems will not last very long. So to predict the life of a helicopter component is an extraordinarily complicated mathematical problem that involves a lot of sophisticated computational modeling. And of course, if you know the details of this computer modeling, you do not want meshes. Otherwise, these meshes would become very complicated and will become unwieldy. So that's the reason we develop meshless methods that Professor Sarler and his colleagues also work on. So these are kind of highly advanced, sophisticated modeling techniques that would make things like this possible. Now I'm going to show you an experiment. This is some music that is put in there. So basically, this is an experiment on a rotorcraft component where a small crack like so ultimately grew and completely severed the component. And this is a meshless modeling of the growth of the crack itself. Okay, so primarily that's how the crack has grown. And so now we have computer modeling methodologies that can predict crack propagation in a fatigue machine such as a helicopter very, very accurately. Now, the same way, when you talk about nuclear non-proliferation treaties or treaties to ban intercontinental ballistic missiles or whatever, the reason why people are willing to sign those treaties is because we have modeling methodologies that can simulate nuclear weapons or ballistic missiles to a degree of sophistication and reliability that testing is almost unnecessary. And that's the reason some countries that do not have serious modeling capabilities will refuse to sign these treaties because they still have to test. But those countries that have enough sophistication to model systems, they do not test systems anymore. And here I'm going to show you an example of a rocket propellant grain that is sitting in a silo somewhere. And so it has not been used for a long time. And so you want to make sure that this rocket propellant grain still will function. And of course, when the rocket propellant burns, if the cracks are there in the system, primarily when the rocket propellant starts burning, then there will be combustion instability and the rocket may fail. So basically, you have the problem of aging of a rocket grain if it has been sitting in a silo for a long time unused. So you want to make sure that, in fact, when you use such a system, it will function properly. And of course, this is all, again, a modeling and simulation problem. There is nothing fancy about it. It is strictly a mathematical problem. And so primarily, modeling plays a significant role. This is, again, a rocket propellant grain where the crack is propagating, and you want to, this is, again, a meshless method of modeling the propagation of the crack in a rocket propellant grain. And this is, again, used for making sure that this rocket propellant grain will function when it is used and if it is used. So this is, now, how computer modeling is used in a very, very pragmatic way, you have now something called integrated structural health management system. Just like a human body, you want to manage the life of the human body and the health of the human body, and you may have a variety of sensors placed, pacemakers or whatever. And just like that in a structural system or any system, engineering system, you want to monitor the health of the system continuously. So you have prognostic tools and diagnostic tools. And so there are systems, embedded sensors and actuators that are embedded in a system that would continuously, mathematically also model how the damage is progressing and compare the damage with the measured damage and see if the system has to be evaluated. The operation of the system should be stopped and evaluated before it proceeds. And these are so-called structural health management systems, which should now be installed in the next 20 years in bridges, airplanes, and everything else. And if you look at what goes into the structural health management system, both the prognostic tools and diagnostic tools are all based upon computer modeling in engineering and sciences. So this is a developing area where everything will be autonomous. The health monitoring of a system will be autonomous. And so if you look at the modeling or the manufacture of a plane in the beginning, you have a power plant system, which is the most critical component of an airplane. And you have fundamental principles, even quantum mechanics, and you have computational fluid dynamics, you have stress analysis, you have ground testing, and in each step, basically you have mathematical and computational algorithms that will guide you the way. And same way, in the existing design and simulation technologies, you start out with computer-aided design, the layout of an aeroplane. How many seats do you want? What is the configuration of the wing, or what is the configuration of the tail, or whatever. And you do a sequential stress analysis of each part and see that each part is designed with the right material and the right dimensions and right damage tolerance or whatever. And then you have trajectory simulations, computational fluid dynamics, damage tolerance analysis, and computer-aided machining. How do you make an airplane part to a desired level of accuracy? And you have rapid prototyping. That means instead of manufacturing the part physically, you may prototype it and see what are the manufacturing operations that you want in that process. And then you have flight simulation. So you have a variety of these technologies, all of which are based on computer modeling by the time an aircraft comes into production line. So this is the existing technology. That means the teams of people working, and if it is a university, maybe a lot of graduate students are working on a variety of these things. And you have non-destructive inspection. Ultimately, we are evolving to a point where you may not want to produce anything to start with, but you produce an airplane on a computer and see how it operates and see how many cycles of life it has before you even produce a single aircraft. And this is the evolving path to virtual reality. And in the virtual reality, you can integrate the design and manufacture and certification and life estimation, everything in a computer, and simulate its design and everything else, life cycle costs, and virtual comparison of alternate designs. And so a team of graduate students can virtually design an airplane, take it through the entire life cycle process, all on a computer, without ever manufacturing it. And so you can couple it with scheduling and whatever else. And so in this evolutionary path, you can start with component levels, and each component can have its own mathematical models, finite element analysis, meshless analysis, or whatever. And you do that for each component, and so you have analysis for each component, and you integrate it through the virtual reality technique to the system level. And then you have virtual assembly, virtual operation. And so all these things will be done on a computer without ever producing a single part, without ever getting a team of designers together. So this is what is going to happen in the next few decades. And of course, there will be more and more people manufacturing aircraft, more and more countries manufacturing aircraft. Take that example, any other system. And so the manufacturing will become global. And so basically, there is no reason for one unit or one country to do this. It can, all this virtual reality assembly can be done by several countries together with several plants and several people operating in different remote locations. And so this is kind of virtual manufacturing. And if you take another system like a bridge, the same thing will happen. Same ideas of life cycle design and everything else. And this is the Minnesota bridge that collapsed 2 years back, and primarily the same thing. Exactly what I said in the airplane will happen in a bridge also. The life cycle design of a bridge can be done in virtual reality. And again, the failure of the bridge is due to crack propagation and loss of structural stability, just like in the aircraft. So whatever we learn from aviation applies equally well in bridges or other systems. And this is a fairly recent event, and events like this happen every day. And so basically, it is estimated that the loss to the world economy due to failures of engineering systems is almost $1 trillion a year. So if you come up with mathematical modeling techniques and design techniques that prevent failure, we can save $1 trillion a year simply due to prevention of failures of engineering systems. Now, here is another example. And of course, Nobel Peace Prizes are given by politicians to other politicians. But if scientists were to design and serve on the committees for Nobel Peace Prizes, we can easily make a case for giving the Nobel Peace Prize to the designer of this fighter aircraft, because history will tell that the Cold War ended due to this plane. And basically, now, ironically, the reason why this plane helped stop the Cold War was primarily because its electromagnetic radar cross-section was so small that nobody can detect its operation. And that's the reason primarily the Cold War ended. And essentially, in designing this plane, if you want to study the electromagnetic radiation from this plane, and if you used finite elements or boundary elements to study this, you did not have the computers in those days, because for those of you that understand a little bit about the operation of electromagnetics, in order to study the high-frequency electromagnetic radiation, the mesh size that you use to discretize this plane must be the order of the wavelength of the electromagnetic wave. And if it is very high frequency, the wavelength is very small. And so you need a lot of computer power to study the electromagnetic radiation from a plane like this, with a lot of edges, which were designed into the plane for that particular reason. And ironically, the mathematics that enabled the design of this plane for high-frequency electromagnetic radiations came from a Russian. But the plane was designed in California. And this Russian eventually became a member of my laboratory, and then we worked on high-frequency sound waves from equally complicated objects. So here, computer modeling takes on a different meaning. It is the computational asymptotics. That means kind of advanced level mathematics on asymptotic methods for electromagnetic radiation that were then put into computational modeling. So this plane was the outgrowth of very, very serious mathematics and computer modeling. And this plane was responsible for ending the Cold War as we knew in the 1980s. And so if you look at an aeroplane, and now you see the aerodynamics and whatever. And if you look at an automobile, and every automobile company spends hundreds of millions of dollars every year to prove that this automobile is safe in a crash situation. That means the passenger is saved from catastrophic injuries if the automobile is in a, let's say, a 30-mile-an-hour crash into a rigid wall. So every automobile company is spending hundreds of millions of dollars using the finite element method to model the automobile, put it in a crash, and so every small aircraft company spends hundreds of millions of dollars in modeling the aircraft to see its aerodynamics and structures are operating well. Now, it all sounds good, but until you come to this modeling business, how to create a model without even running on the computer, the creation of the model is a labor-intensive process that nobody in North America or Western Europe is willing to do. So most of this model generation is done in Bangalore, India, or in Shanghai, China. So basically, this modeling has become an offshore industry. So basically, then so most of the jobs of this size are performed outside the US or outside North America. And so this motivated the development of so-called meshless methods. So can we get rid of this labor-intensive process of generating a mesh and come up with alternate modeling strategies that would still make possible to study aircraft and automobiles and microsystems or whatever without a mesh? And that is the whole idea of this meshless methods, which I started out with a few years back. And now, why do we use these meshless methods? Well, if you have an aircraft and an automobile that is fairly, retains its shape during the operation, an aircraft is not going to deform or distort during its operation. Likewise, an automobile is not going to distort too much in the operation unless you put it in a crash, and then you have a big mesh, and you want. But suppose you want to analyze motion of, or study the motion of very, very flexible things. And what is more flexible than a fish? So I'm going to show you how these meshless methods are essential in analyzing motions of very flexible things flowing in water. And so here is a jellyfish that, that most people are interested in seeing how it moves. And so this is a fish that moves around because it flaps and it is very, very flexible. And how do you study the motion of this fish? And how do you see how it moves around? And so if you look at jellyfish or fish in general, they're very flexible objects that are moving around. And there is no mathematical methods or any mesh-based method that could analyze this jellyfish or the other fish that are moving around. So I would like to show you how these systems motivate the development of, well, why do we study jellyfish? Well, maybe we'll come up with systems that move like jellyfish and devise engineering devices that operate like jellyfish or operate like fish in water or in air or in some other medium. So here is an example of how mathematically you model the jellyfish and see how it moves. So primarily, essentially, the jellyfish is something like so. You can describe its shape mathematically. And then you kind of see how this surface moves around. And then you study how the fluid dynamics of this system, how the fluid moves around due to the flapping of this very, very flexible membrane of the jellyfish. And without going into too many details, I can assure you that there is no way you can study this problem by any mesh-based method. And so it's only the meshless method that would allow you to do that. So here is an example of a numerical simulation of the motion of the jellyfish. And here is the, I don't want, anyway, that red line is the outer membrane of the jellyfish, and it is contracting and expanding, and the fluid that is being moved around is creating an upward motion of the jellyfish. So we are now able to see how the motion of the jellyfish itself can be modeled, and how we can learn from these flexible systems and how they move in fluids. So without mathematical models like this, it will be very hard to understand the motion of a fish. And once we understand the motion of this fish, we can now biomimetic engineering. That means we can mimic these jellyfish and create an engineering system that would serve a useful function in moving through air or water. And so this is an example of how the so-called meshless methods that me, my students, Professor Sarler, his students work on are ultimately useful for developing engineering systems. And there is no other method that could do this thing. Now, on the other hand, if I were to look at a fish itself and see how the fish moves, and this is a subject that a lot of engineers are now interested in. Here is an example, mathematical model of a fish. And I won't go into the mathematics. And the vertical velocity, that the equation that I wrote there, simulates the undulatory motion of the fish and how the tail moves and the head moves and so on and so forth. The whole idea is, if we were to simulate this motion and see how the lift and drag are generated and how this is moving, then we can create an engineering system, an intelligent engineering system that could swim like a fish and do some useful function, a micro air vehicle or whatever, that engineering systems that we could. So we want to simulate the motion of this fish and see how the vortices are generated and this is now a complicated mathematical problem which cannot be solved by any method other than a meshless method. And here is, again, some details of this method, which, without going into too much detail, this is essentially simulating the undulatory motion of the fish and see how the surrounding fluid generates vortices and lift and drag. And again, this is only a very, very recent development, which was thought to be impossible to analyze by any other method. But we are now able to solve such problems by the so-called meshless methods. So primarily, any complicated process can be modeled. And the idea is not just the fun of modeling, but to learn something from this modeling and create a useful engineering system that would perform a function that would ultimately benefit mankind. And so primarily, there are, this is now a kind of a little bit of the details for those that are familiar with such technologies. And all these are based on mathematical methods. All these meshless trial functions for mathematically complete and continuous and so on and so forth. And there is a variety of these. And likewise, there are a variety of meshless methods. But all of them are rooted in this fundamental idea of the meshless local Petrov-Galerkin method. And that's what we have been developing. And these are the schematics of these meshless methods, and I won't go into too many details. And so basically, as I showed you in the case of the jellyfish or the fish or whatever, these meshless methods make it possible to model complicated systems that were otherwise thought to be impossible to be modeled. And here is another example of a bullet piercing through a metal. And primarily these methods of penetration and whatever. And likewise, if you want to dispose nuclear waste into the ocean, how do you shoot the nuclear waste into the ocean floor? How deep does it go? And these are all mathematical problems that can only be analyzed by such meshless methods. Now, going beyond mega systems, as I mentioned, the future is at the intersection of life sciences and engineering, physical sciences, medical sciences, and information sciences. And primarily, life sciences are biological sciences and behavioral sciences, and you put them all together, and what is emerging is systems engineering in biotechnology. And this is where incredible advances will be made in the next few decades, and hopefully in my lifetime. So you are talking about modeling molecular motors protein motors, how chemical energy is converted into mechanical energy, and how this can be used in driving nano systems, and how to understand the functioning of the cell, and how does mechanosensitive channels in a cell aid in various processes. These are all nano systems in biology that biologists are trying to study, and engineering would play a dominant role in the understanding of these biological systems. And how do you model molecular motors? How do you understand the conversion of chemical energy into mechanical energy through a protein motion? And these are done through molecular dynamics and Langevin dynamics, which are, again, modeling methodologies in the computer. And so when you put engineering and life sciences together, the paradigm is more than Moore. Moore being Gordon Moore, who is the Intel's chief technical person. And so how do you design chips that are more than Moore? And so we are entering into an era of bio-MEMS, bio-microelectromechanical systems, bio-NEMS, lab on a chip, life chip, and so on and so forth. Lab on a chip essentially is based upon fluid dynamics at a small level, microfluid mechanics. And how do you study flow through microchannels and create useful devices out of it? And basically, now there are a lot of companies within a 50-mile radius of my university. My university is located in the medical device capital of the universe. Everybody there wants to do bio. A lot of venture capitalists investing money in bio devices. And of course, to understand flow through these microchannels, you need to understand microfluid mechanics. And of course, it is not continuum fluid mechanics, and it involves Monte Carlo simulations and lattice-Boltzmann methods and other. And this is an example of a lab on a chip made out of paper by a professor at Harvard University, George Whitesides, a very extraordinarily brilliant man. And he came up with this simple paper device that could be used in poorer countries in Africa, where they could perform diagnostic tests simply using this paper device. Well, how do you analyze, how do you calibrate this macro device? Well, again, modeling and simulation based upon molecular dynamics, lattice-Boltzmann, whatnot, play a significant role. And indeed, some students in my lab are trying to calibrate these devices. But and likewise, we have electronic counting of blood cells, lab on a chip. And lab on a chip, based on microfluid dynamics, is going to be a growth industry in the next 2 decades or so. This is, again, where engineering would play a dominant role in diagnosing diseases and other. So you have, again, microfluid mechanics, microsolid mechanics, and lattice-Boltzmann methods, molecular dynamics will all play a role in the design of these devices. And likewise, more and more microfluidic diagnostic devices. And then we have life chips coming up. And a life chip means if we take a single cell in a human body, how is it affected by disease? And you can now show that a single cell in a human body, as is affected by disease, will change its mechanical properties and how it deforms. So you can use inverse computational modeling to see how a diseased cell would behave. And a life chip is something that would take these variations or heterogeneities of the single cellular response and try to infer disease from that. And so these life chips also are now more and more research is being done on these, and computer modeling would make a dominant place, would play a very significant role in the analysis of a single cell and how disease affects it and so on and so forth. And then you have biomimetics, which is mimicking nature to make engineering possible. And we all know this cat's eye that is used in the roads, and the Velcro that was designed in 1948. And biomimetics, again, mimicking nature, whether it is the motion of a jellyfish or a fish or a butterfly or anything else, how to design micro air vehicles based on this is something that will be done in the next 10, 20 years. And then when you come down the length scale, the carbon nanotubes and how they are going to play a dominant role in designing devices and how computing plays a role. This is a single-wall carbon nanotube, and there is a multi-wall carbon nanotube, and that is a carbon nanotube composite that now carbon nanowall composites are now becoming more and more common. How to increase the interfacial strength in a composite by using nanotubes. And all that, of course, apart from experimentation, which is more expensive and more time-consuming, modeling and simulation based on molecular dynamics, lattice-Boltzmann, or equivalent continuum methods, these are now common occurrences. And of course, carbon nanotubes, whether they play a role in strength-based devices, in functional devices such as transistors and sensors to detect hazardous gases, etc., are now going to play significant roles. And to study these devices and how they are made, once again, if you go through this scientific literature, they are computationally intensive, and modeling plays a dominant role. And of course, carbon nanotubes, super muscles, how to use carbon nanotubes in making artificial muscles, and how to use carbon nanotubes as TERFs, as thermal switches in MEMS devices, and how to analyze them, again, is significant. Now, the last thrust where computational modeling is going to make a very significant impact is in the so-called design of materials. As Dr. Thompson said, human civilizations are normally characterized by the materials they use, and I think our generation and this next century would be characterized by a new materials age. There will be a brand new class of materials that will be designed from bottom up, from each atom to the macro level, and from top down, from the macro level to the bottom. And this is the so-called idea of materials by design. And these are structural materials, ceramics, polymers, or composites, are functional materials, electronic, magnetic, chemical, or optic. So the whole idea here is, how do you come up with a material, not by laboratory mixing and matching, but by mathematically building up from atomic property level to the top for a given structural strength, stiffness, fracture toughness, electromagnetic properties, electromagnetic absorption, or whatever. How do you design materials from atomic or quantum level? And so once you design materials, you can have intelligent materials that remember their state 10 years back or 5 years back, or how they are deforming. You'll have multifunctional materials, the materials that do sensing and actuation and load carrying or whatever. And then you may have self-healing materials. Just like in a human body there is a cut, the cells migrate to the sign of the wound and heal the wound. Likewise, can we design materials that may have some other material that can be made to move to the site of the damage and heal the material? And of course, already there are polymers that are being designed to heal themselves. And these self-healing polymers will be used in biomechanical devices. And then we also have intelligent structures, that means autonomous structures that would sense their deformation and take action to control that deformation. And adaptive systems with integrated sensors, actuators, and electronics. And all these come under the category of materials and materials by design, intelligent, smart materials, smart structures, self-healing materials. And of course, these are not just scientific fiction. These are realities. There are a lot of laboratories in the world are working on them. And this is kind of a artist's conception of what a self-healing material would be. That means if you have a car that is going on a road and the material damages and due to some road interaction, and so you have a self-healing material concept where not only the automobile part, but the road itself will be healed by itself. And this is closer to reality, and it's almost in another decade or so, these things would be possible. And so basically you have virtual reality again, just like automobiles, you can have virtual reality for materials by design. That means you can design a material for a given set of properties, starting from the nano, meso, micro, macro level, learning the structure property relationships. And then you'll have multi-scale computational physics and chemistry, atomic force microscopy, virtual fabrication. And there are lots of laboratories in the world that are working on this, including my own university. And so I gathered about 100 very smart people from all these 13 places, 10 universities and 3 campuses, and had a 4-day workshop on materials by design. So I asked all these 100 people, I mean, each one works in a different area, each one sees the subject in his own or her own way. These are all very, very smart people. And I asked them to put down what are all the things that they think would be ultimately needed in this paradigm of materials by design. And that's what they suggested. This is a composite picture of what 100 people thought would be needed to design materials from bottom up. And so if you look at most of those things, computational chemistry, quantum to continuum, level sets, theory of complexity, whatever, and you see those lists, and essentially what will turn out is that computer modeling is the dominant theme that goes through this, dominant thread that goes through all this research by 100 very, very smart people on how to design materials from bottom up. So basically it all boils down to methods of computer modeling in engineering and sciences. So it's not just me, but there are hundreds of people that have very smart ideas on how to do this. So basically, when you talk about advanced materials, which will define the age we live in, advanced materials themselves, again, you have nanostructure, property relationships, multi-scale modeling, synthesis and processing. All this will be done mostly on the computer, no laboratory. And of course, all this cannot be done by one single laboratory. Maybe hundreds of laboratories will be involved. And they are all linked by computers and basically international research facilities. That means it may not even be done by a single country. And so this whole idea of research and education in materials, which will dominate the next century, will be done by computers. And again, the so-called nano imprinting process, which would change our lives significantly in the next 20, 30 years. This nano printing process is also, imprinting process is also for lithography. And this also is dominated by computer modeling. And in my lab and others around the world, the molecular dynamics models are used to simulate this nano imprinting process and essentially come up with the process definition itself. How do you define the process to come up with the right imprinting? And so, so-called desktop manufacturing, on a nanoscale, that means you do not have a real factory somewhere, but it's all on a desktop. All this will be done by computer modeling and simulation. So in a sense, the reason why I started this journal with the title Computer Modeling in Engineering and Sciences about 12 years back is because of my conviction that this discipline would play a significant role in product development, process development, integrated product and process development, and will have a significant impact on the economies of the world. And I would like to end this lecture with the thought that even though we think in 2009 that we have evolved with all these years of education and lots of university research to talk about mega to nano, it turns out that a long time back, maybe 800 years before Christ, if you look at the Upanishads, the teachings of the rishis and the teachings of the sages living in the mountains and hills and the rivers of India, and if you look at the Upanishads and read what they had to say, they also had something to say about mega to nano. And this is what in Rig Veda, the Upanishads, that's what the quotation was. The wise man looks into space and does not regard large as too large, nor small as too small, for he knows there are no limits to dimensions. And this was 800 years before BC. So that means human mind has been thinking about mega to nano and how to use small to large for the benefit of mankind for a very, very long time. And of course, this mega to nano will also dominate in the next century, except, maybe more and more nano devices will be made, especially in the area of human health, because human health is the biggest frontier. And now people say that a baby born in California in 2009 most likely will live 100 years. I mean, that is statistically the guess. So by 2050, it may come to the point with the development of nanotechnology, drug deliveries, and engineering and medicine and whatever, we may come to the point where human beings will live 200 years. Maybe we are approaching the limit of immortality. Maybe we may never die, but I'm sure that I will die. With that, I will end the lecture. Thank you.